All right, so tonight's thing is we're going to start with relations and functions. Okay. All right, so we're going to start off with just a little bit of writing, and then we'll get to some like examples. Okay. All right. So first, I'm going to define what a relation is. Okay. So definition: a relation. Okay. I'm going to underline it because that's what I am defining. It is a set of ordered pairs. Okay, that's what a relation is. That's all it is. It's just a set of ordered pairs. All right, so let's just get an example of one. So the set, one comma two, comma two comma four, comma three, 3 comma 6, 3 comma 6 is a relation. Okay. So I just have a set of ordered pairs. So you look, each thing in this set, 1 comma 2, that's an ordered pair. 2 comma 4, that's an ordered pair. And 3 comma 6 is also an ordered pair. So I just have a set of ordered pairs, and that is a relation by definition. All right, so here's an example of one. All right, so we just need some more terminology. So here we go. So the set consisting of the first components. The first components of each ordered pair is called the domain. Okay. So let's just use our example from before. So the second, so the domain is just going to be the first component of each ordered pair. So look, 1, 2, and 3. Those are the first components of each ordered pair. So let me just put those first components in a set. All right. So that would just be 1, 2, 3. Okay. So that is the domain of the first example. Okay. Of the previous example. All right, so I hope everyone sees how I obtained the set 1, 2, 3. I just took the first ordered pair, the first component of each ordered pair, and just stuck them in a set. All right, so that's the domain. All right, so we also have a name for the second component of each ordered pair. So let's just get that out of the way. So the set consisting of the second components of each ordered pair. So the name of this is called the range. All right, so we also have a piece of terminology for the second component of each ordered pair. All right, so let's just talk about what the range would be of the previous example. So the range of the previous example is, all right, so all I need to do is just look at the second component of each ordered pair and just throw them in a set together. So the second component is, the second components are 2, 4, and 6. All right, so I just put those numbers in a set, and that will be the range of that example. All right, so I hope that's pretty straightforward. Okay, so just some more terminology. All right, I know it's a lot of writing to begin. So each element of the domain, so each element in that set is called an input. Okay, so let's go to domain, 1 is an input, 2 is an input, 3 is an input. All right, so each element of the domain, we just call that an input. All right. All right, we also have a name for each element of the range. Each element of the range is called an output, all right, which shouldn't be too surprising since the domains were called inputs, so we call the range the outputs. All right. All right, so I'm just setting up all of this terminology so I can use it later on, okay? All right, so we have relation, we have all of this terminology set. Now we'll actually get to the definition of a function, okay? All right, so here we go. So very important, definition. So a function, so I'm gonna underline that because that's what I'm defining. Okay, a function is a relation, so it's a special type of relation in which each possible input leads to exactly one output, leads to exactly one output.
So it's sort of like an equation.
Yes, I think so. Essentially, like one input cannot have two outputs. Okay, so that would violate the definition of a function. So we're going to see some examples that are functions and that are not.
Got it.
But yes, functions can be defined in an equation form, which we'll do later. But yeah. All right, so the relation. So let's see this example, the relation. So I'm just going to write down an example, 1 comma 2, 1 comma 3, 2 comma 7 is not a function, not a function. All right, so let's just think about why this is so. Well, to be a function, each input has to have just one output. All right, but something is wrong here with the input of 1. The input 1 has 2 outputs. The input of 1 has an output of 2 and an output of 3, okay? So that violates the definition of a function. All right, so I'm just gonna write that because the input 1 has 2 different outputs, all right? Has 2 different outputs. All right, so I hope everyone sees that. I have the input 1 going to 2 distinct elements. It's going to 2 and it's going to 3. That violates the definition of a function. All right, how about this one? How about this one? Okay, the relation 3 comma 4, 4 comma 5, and 6 comma 100. This is a function. This is a function. Okay. Because each input has exactly one output. Excuse me. All right. Yeah, so pretty much none of the input values are being repeated. 3 is going to 4, 4 is going to 5, 6 is going to 100. Each input, 3, 4, and 6, is just getting sent to one output, exactly one output. All right, so this is indeed a function. Okay, so next, we can also represent relations in a diagram. Okay, so we can also represent relations in a diagram as such. All right, so I just need to go over to my images here and just place it on the notes. Just give me a second. Okay, so I hope everyone can see this image that I just pasted. Okay, so let's just talk about each of these guys here on this figure. So the first one, we have the inputs P, Q, and R, right? And P is going to one output, Q is going to one output, and R is going to one output. So this is fine. This is a function, okay? This is a function, okay? Because just each input is going to one output. Similarly, the middle one, the input P has one output of X, the input Q has one output of Y, R has one output of Z. So that works. All right, but the last example here, you'll see that Q, the input, look, it has two outputs, okay? So in C, Q has two outputs, okay? Thus, this relation is not a function, okay? Because we require each input to just have exactly one output, okay? But Q has two outputs, all right? So C has two outputs, so it's not a function. All right, so I hope everyone is seeing what's happening here. So C is not. So C is not a function, okay? Cool. All right, so let's get to some, just some language and terminology, all right? So how do we speak about functions in practice here? All right, so basically, given a function, we usually say, so in quotes, the output is a function of the input. All right, so that's just how we say it. So like I'll write that kind of often. So given a relation, or no, given a function, we'll say that the output is a function of the input. All right, so let's actually see this in practice. All right, so here's a kind of cool example. So let's consider the following menu from a coffee shop. All right. From a coffee shop. All right, so let me just write this out very quickly. Okay, so I'm just going to write a menu with food items and their corresponding prices. All right, so we'll say that a tall coffee has a price of $1.49. Okay. We'll say that a grande coffee will have a price of $2.05. Okay, $2.05. And the last thing, we'll say that a glazed donut, which is very yummy, by the way, will have a price of $1.49. Okay, so this is just a menu. It has food and prices. Okay, so this should seem familiar. So now I pose a question to you guys. Okay, question. So in this menu, so I have two questions for you guys. Well, yeah, so here's the first one. In this menu, is price a function of the item? Okay. Is price a function of the item?
No.
Well, so this is asking
Like there's two outputs, they're the same thing, right?
right.
No, but you have two different inputs for the same
But
amount.
that's okay though, because tall coffee is going to 149 and glazed donut is going to 149. That's fine. You can have two different inputs going to the same output. You just can't have one input going to two outputs.
Oh, okay.
Yeah. So the answer is yes. So I know this is a little tricky. So is price a function of the item? Meaning, if the items are the inputs, are the prices the outputs? In that setup, does this qualify as a function? It does. Because look, each input here, coffee, donut, they're just going to one output. Okay. So the answer here is going to be yes. And the reason being, each food item has only one output price.
So whenever you use the term function of, you're just asking that is that the output of the input?
Okay, so function of, whatever comes after of, that's the input.
Oh.
Yeah, function of the item. So in this case, the item, the left-hand side of the menu, those are our inputs. Okay. Next question. So now let's flip it. Okay. Is item a function of the price? Function of the price. All right, so let's just take a moment to think about this. I'll scroll up. So I'm just going to erase these arrows that I had here, okay? So we're asking here, is item a function of the price? So if we make the prices our inputs and the outputs our food, is this a legitimate function? So let's think about it for a second.
No.
Yeah, okay, so does someone want to explain or tell me what's up?
Well, if the prices were the inputs, two inputs, one input would have more than one output. 149 is tall coffee and the glazed donut.
Correct. Exactly. So we do have a problem here. We have 149 going to two different things. Exactly. So we have 149 going to tall coffee, but it's also going to glazed donut. Exactly. Very good.
That would actually be kind of a sweet deal. I get both of them.
Yeah, right. Exactly. That is a good deal. Yeah, so let me just explain. So I'm just going to write that. So the answer is no, because as Jen said, the input of $1.49 has two outputs associated to it. Okay. All right, so that's going to violate the definition of a function. All right, very good. All right, so we can also talk about relations in table form. So let me just talk about that quickly. So relations in table form. So it's kind of similar to this menu that I have written up. So let me just go to, so I just have to go to my images and cut and paste it. So just give me a second. Right, yeah, so we can also represent relations in a table. So remember we had like ordered pairs. Well, just in this setup, the ordered pair would be -3, 5. The other ordered pair would be 0, 1, and the other one would be 4, 5. Okay. So we can also represent relations and functions in table form, like so. Okay, so first of all, would someone like to, so I'll call this A and I'll call this B. So is A function? So that'll be yes or no. And similarly, is B a function? All right, so let's just take a second. So let's just look. And if someone would like to tell me, that would be great.
I'm going to say table A is, would be, is not.
Table A is, you're saying?
Yes.
That is correct. So why is table A a function?
Because table A has unique outputs to each input.
Yes, exactly. Each input is just going to one output. Very good. And how about B? So would someone like to tell me about B? No.
It's not a function.
Right. B is not a function. Thank you. Thank you, Vincent. Yeah, B is not a function. You just want to explain why quickly?
Yeah, because you have two inputs that are the same.
Right. Exactly. I have two inputs, but really what needs to be also said is that you have two inputs that are the same. They're going to different things. Okay, 5 is going to 2 and 4, which is bad. Right, but yes, thank you. Very good.
Is it a possibility in like situation like in a problem we need to like for homework like be 5 input and 2 output and then 5 input and 2 output again and it's still a function because well it's the same but like is it something that like happens often or
Are you so I'm not
like a trick
I'm not sure if
like
you're
a tricky question?
Yeah, are you saying is it often that we'll encounter relations that
Yeah.
aren't functions?
No, there are functions, but like they're just like there to trick us, like 5 input and 2 output, and then repeat it 5 input and 2 output. So we see like 2 5s in the input and think it's not a function.
Right. Yeah. So just a good visual way to see it is if you see the same input being listed twice, it's going to not be a function.
Okay, so it's not something. Okay, thank you.
Yeah. But like if I change this 4 to a 2,
That's what I'm talking about. Yeah.
okay.
That would still be a function, right?
This would be a function. Yes.
Yeah, that's what I'm talking about. Yeah.
Yeah, this would be a function. You're just being kind of like redundant. You're just listing your elements twice for some reason. But yeah, that's a
Like
good.
just to fool us.
Yeah. Good. All right. Yeah. So on the homework and stuff, you're going to see functions in table form like this. So I just wanted to get everyone familiar with that. Okay, let's keep going. So now we just need to talk about notation. So symbols, in other words. So function, notation. So how do we write these things in mathematical symbols? All right. We will usually define a function using letters such as F. Okay, so that's just conventionally what we use to denote a function. We'll use the letter F. It doesn't have to be F. It can be like G, H as well. But if the letter F is not being used, I'll most likely use F to denote a function. All right, so let's just see what that looks like. So here's a definition. The notation y equals f of x. Okay, so y equals f and then in parentheses x defines a function named f. Okay, so we're going to call this f. All right, how do we read this? This is read as, so how do we read this aloud? Y equals a function of x. It can also be read as y equals f of x. Okay. Okay. So just more writing. The letter x denotes the input. Okay, that's the input of the function x, and the letter y or f of x denotes the output. Denotes the output associated to the input x. All right. All right, so hopefully this seems somewhat familiar from like a high school math class. All right. All right, so let's do an example utilizing this new notation. All right, let's do an example. All right, so the function days equals f of month, okay, or d equals f of m for short, okay, defines a function that takes a month as an input, okay, and outputs the number of days in that month. In that month. All right, and we're going to exclude leap years, right? Because maybe someone can answer me why we want to exclude leap years in this discussion. Okay, so I've just defined a function, f. It takes an input a month, and its output will be the number of days in that month. So for example, f of January will just be the number of days in January. All right, so that's going to be 31. All right. Okay, and f of February. How many days are in February? That is 28. Okay, so does someone want to answer me why I wanted to exclude leap years? Why would that be bad if I had leap years?
2 different outputs to 1 input.
Exactly. So if I allowed leap years in this discussion, February would get mapped to 28 and 29, making it not a function. All right. And then just one more, f of June, that will be 30. All right. And so on. So you can fill in all of the values of this function. All right, so this is an example of a function, and we're using our notation f of something equals an output. All right, and let's just quickly talk about the domain. So here, our domain, so remember, the domain is just all the possible inputs of our function. So here, our domain is all of the months, okay? And our range is, okay, so the range is just all the possible outputs. So the only possible choices for number of days for a month to have is just 28, 30, and 31. So I hope that makes sense. These are the only values that our function will output. It's going to be one of these three things, 28, 30, or 31. Okay, and that's why we're excluding leap years, so 29 is not in this set. All right, so I hope that's okay. So just please stop me if anything is not clear.
So just to clarify really fast, we could kind of clarify the domain as all the possible inputs and the range is all the possible outputs.
Right. Yes. So our domain here would be January, February, March, April, May, June, and so on up until December. Okay, so the function, yeah.
True for every single function, is there always going to be a set range and domain?
When you say set, range, and domain, are you talking about like a finite set? No. No. So we're going to see that next, actually. Okay, so the functions we're going to deal with in this class are not going to really be like stuff like this. It takes in January and outputs 31. This is just a very instructive example. All right, this is just to utilize our new notation and ideas. However, so the functions we will deal with in this class are ones that have real numbers as both inputs and outputs. Okay. So those are the functions we're going to be dealing with. So the output, so the input and the outputs, so the domain and range are going to be the real numbers. All right. So here's an example. Here we go. F of x equals 2x. That's an example of a function that takes in a real number and it also outputs a real number. Okay, so let me just write that. So this function takes in a real number x as an input and multiplies it by 2. Multiplies it by 2 as an output. All right, so that x there, that's the input, and then the 2x, that's the output. All right, so what this function does, it just multiplies numbers by 2. All right, so let us now evaluate f of x with some inputs, okay, with the inputs, with these inputs, 2, w, and a plus h. All right, and when I say evaluate f of x at these inputs, I mean I want to just plug in 2, w, and a plus h into our function and see what they will output. All right, so let's do a. So let's plug in 2. So f of 2, it's going to be 2 multiplied by 2, which is 4. Because this function, remember, it takes in a number and multiplies it by 2. Okay. All right, well, how about w? So f of w, that's just going to be 2 times w. Okay. All right, and the last one, f of a plus h. So nothing's different here. You just take the input and you multiply it by 2. It's just going to be 2 multiplied by a plus h. And then if you want to go a little further, you can distribute the 2 into both terms. So you can just distribute the 2 into the a and h. It'll be 2a plus 2h. All right, and here a, h, and w, they're just fixed numbers represented as letters. All right. All right. So any questions?
For 2w, where did you get the 2 from?
So this function, remember,
Oh, okay, from that one. Okay.
2x. Yeah, it just multiplies the input by 2. If the input is w, the output will be 2 times w.
Okay, gotcha.
All right. Trying to think if we should do another one. All right, let me just do a quick example again. All right, so evaluate the function. All right, so here's another function. F of x equals x squared minus 4 at the values 1 and 2. Evaluate the function f of x equals x squared minus 4 at the values 1 and 2. All right, so the first, let's just do f of 1. So f of 1 just means wherever I see an x, I plug in 1 in for that. So that's going to be 1 squared minus 4, which is just 1 minus 4. which is -3. Okay, so you just plug in 1 wherever you see an x in the formula. And then similarly, f of 2, okay, wherever I see an x in x squared minus 4, I just put a 2 there. So that's going to be 2 squared minus 4, which is 4 minus 4, which is 0. Okay. All right, so I hope that's okay with everyone. All right, next, we're just going to talk about graphs of functions. Okay, so given a function, f of x, we can graph it on the Cartesian plane, so the xy plane. We can graph it on the xy plane by plugging in a few x values and plotting the corresponding points. So this is kind of similar to when we were graphing lines. We like set up a table with some input values, and then we put their outputs, and then we plotted them on the plane. All right, so let's just quickly do that. So the example will be to graph f of x equals x squared minus 1. Okay, so first, make a table. First, make a table. So my first column will be our inputs x, and our second column will be the outputs y equals f of x. Okay, and the inputs you want to choose, it doesn't matter completely, but usually I like to just do -2 to +2 and everything in the, all the whole numbers in between. So -2, -1, 0, 1, 2. All right, so these numbers in the left column, I'm going to be plugging in to our function. Okay, so if I plug, -2 into our function, you do -2 squared minus 1, which is 4 minus 1, that'll be 3. If I plug -1 in, I will get 0. If I plug 0 in, I'll get -1. If I plug 1 in, I will get 0. And if I plug 2 in, I'll get 3. All right, so so any questions as to how I obtained the numbers in the left, in the right column? All right, and then the rest is easy. So now just plot these points. Okay, now just plot these points. All right, so let me see if I can draw something halfway decent. Okay, so the first input is -2, 3. So we know how to plot points on the Cartesian plane now. So I just go to -2 and I'll go up 3. So it's going to be like around there. -1, 0 will be right here. 0, -1 will be right there. And then we have 1, 0 and 2, 3. Yeah, so something like that. And then you're just going to connect your dots with some sort of smooth looking curve like that. Okay. All right, so that's kind of how you graph something. Okay, so hold on, someone wrote something in the chat. Yes, this is a parabola, Saeed, exactly.
Are all functions like parabolas, or can like a curve, right? Yeah. Or can they be like a straight line, like an equation?
Yeah, so remember the lines that we were dealing with last week or so? Those are also functions. So
Oh, okay, okay, great.
Yeah, so I was actually just gonna get to these other functions, so it's good that you said that. All right, so so now I'm just going to introduce some very commonly used functions. Okay, functions that we're gonna call upon in class very often. All right, so let me just write a little bit. So here are the graphs of the so-called toolkit functions. Toolkit functions. Okay, and these are also called parent functions in some books, also called parent functions. Okay, they both mean the same thing, also called parent functions. Okay, so here are the graphs of the so-called toolkit functions we should be familiar with. All right, so I'm just going to introduce that now, that we should be familiar with. All right, so let me just go to my images here. Just give me a second. Why are, oh. Yeah, I think I lost that image. All right, just give me 1 second, guys. I'm sorry. Let me just go and get this back. Lecture 6, toolkit functions. Okay. Okay, so here's one, and I just need to grab one more image. Sorry for the delay. Okay, so let me just talk about each of these functions. So here are the toolkit functions, okay? So just have them written here. You don't have to write this down because this is going to be included in the notes that I upload, but I'm just going to talk very briefly about each of these guys. So we have the constant function, f of x equals c, and c is any number. So you have here on the right side, f of x equals 2, okay? Similarly, we have the identity function, which just takes an input, does nothing to it, and outputs that. F of x equals x. Okay, so it just outputs exactly what you inputted to it. And that actually is the equation of a line with slope 1 and y-intercept 0. Right. Okay, we also have the absolute value. It takes in a number and returns its distance from 0. Essentially, it just gets rid of the minus sign if there is one. All right, so if you plug in -2 into this guy, you get back 2. Okay, we have the quadratic, which is x squared. It looks like this. And then we have the so-called cubic, which is x cubed, or x to the 3rd power. All right, so we're going to be referencing these functions a lot. So I just wanted to introduce them, okay? And these are the so-called toolkit functions, or also called parent functions. All right, so I hope that's okay. All right, good, good. So now let me get to the vertical line test, okay? The vertical line test. Okay, so what is this? This is a quick test to see if a graph is a graph of a function. is a graph of a function. Okay. Okay, so this is useful for when you're given a graph and you want to decide whether the graph represents the graph of a function. All right. All right, so here are the steps for the vertical line test, and then we'll do some concrete examples. Steps. Okay, 1. Inspect the graph and see if any vertical line would intersect the curve more than once. More than once. That's the first step. All right, so you essentially just draw vertical lines all throughout your graph, and you see, okay, you ask yourself, do any of these vertical lines cross the curve more than once? Well, if so, if there is such a line, if there is such a vertical line, what's the conclusion? The graph does not represent the function. Does not represent a function. All right, because a vertical line touching the graph in 2 places would mean that one input actually had more than one output. Okay, so let's now do some examples. Let's use the vertical line test. So let me just go to my images here. I don't lose it this time. No. Okay, so the first one, this is going to be a function because as you can see, any vertical line I'm just gonna make this a little bigger. Yeah, so any vertical line that I draw through this graph, it's only going to intersect the graph once. All right, so this means that each input is just having exactly one output. That's the interpretation. Okay, how about this middle one? This is not a function because as you can see, there is a vertical line that touches the graph twice. Okay, so this input here, this x value, has gotten mapped to 2 outputs. And that's what violates the definition of a function. We have one input going to 2 outputs, so it's not a function. It violates the definition. Same story with this third guy. This input here has gotten 2 outputs, okay, here, and it also gets outputted here. Not a function, all right? So no and no. All right, so the vertical line here has crossed the graph twice. So we can safely conclude this is not a function. All right, very cool. All right, so any questions on using the vertical line test? There will be practice with this on the homework. All right. Next thing, we're going to talk about one-to-one functions. Okay, so let's start off with a definition. So what does it mean to be one-to-one? All right, a function is said to be one-to-one, 1-1, or injective. All of these things mean the same thing. So a function is said to be 1-to-1, 1-1, or injective if each output, okay, each output in the range has exactly one input that mapped to it. Okay, so it's sort of like the definition of being a function, but from the perspective of the inputs. Okay, so in this setup, so a function is one-to-one if each output just had one input that got mapped to it. All right, and now let me just, so there are other ways of saying this. All right, if that was a little confusing. So this can be equivalently rephrased as such. Okay, so there's three. Right. Okay, so there are three other ways of saying the same thing. Okay, first way is that distinct inputs get mapped to distinct outputs. Distinct outputs. Okay? So in other words, if I have two different elements in the domain, I know that their outputs in the range will also be different. Okay, another way of phrasing this equivalently. If f of x equals f of y, so if two outputs are the same, well then it must be the case that the inputs were the same to begin with. Then x equals y. Okay, so these are all equivalent ways of saying that a function is one-to-one. All right, so this is the same as that. And thirdly, is just a symbolic representation of number one. If x does not equal y, then f of x does not equal f of y. So I hope everyone can see that 1 and 3 are the same thing. 3 is just the symbolic representation of 1. Okay, so x not being equal to y means that the inputs are distinct, and f of x not equaling f of y is saying that the outputs are distinct. Okay. All right, so all of these things just mean that a function is one-to-one or injective.
And that's for every input on the table or graph.
Yes, this needs to work for every single input. Exactly. Okay, so go back to first root. Right, okay, so I'm gonna go back to earlier and we're going to compare. Let's see, where was that picture? Yeah. Okay, hold on. Okay, so here's the picture from earlier. Okay, so is A, well, okay, first of all, C is not a function, so this is not even going to be considered in our discussion. Okay, A. A is not going to be one-to-one. Reason being is that the output of N had two inputs that went to it. Okay, so in other words, we had two distinct outputs, Q and R, that got matched, that got mapped to the same output. Okay, so A is not 1-1 because Q and R have same output. Okay, so I hope everyone sees that Q and R are distinct distinct elements in the domain, but they have the same output. So that violates one-to-one. Okay, but B is one-to-one. And you can just see that visually by inspecting this, okay? Each input, each distinct input has a distinct output. In other words, each output just has one arrow coming into it. Okay, so each output has exactly one arrow coming into it. Okay. Okay, so we also have a nice test to check for one-to-oneness or injectivity, and that's called the horizontal line test. Horizontal line test. Okay, and what does this do? It allows us to deduce quickly whether the graph of a function represents a 1-1 function, a one-to-one function. All right, so it's in the same spirit as the vertical line test, except we draw horizontal lines instead. All right, so let me just write this out formally. But it's basically the same procedure as the vertical line test, except that you draw horizontal lines. All right, step 1, see if any drawn horizontal line would intersect the graph more than once. More than once. Step 2, if there is such a line, if there is such a line, the function is not, sorry I'm writing so sloppy, is not one-to-one.
And this would be when it's crossing the y-axis, I think, right? Or it could be both, I mean.
Yeah, so the horizontal lines you draw don't need to be the y-axis. They'll be parallel to the the lines you draw will be parallel to the x-axis. Yeah.
Right.
But I think it'll be cleared up once we do an example here. All right, let's see, where are we at? Oh, is this what I wanted? Okay. Yeah.
Oh, okay, so.
Okay. So let's use the horizontal line test. So let's look at A first. All right, is A, the graph of A, is that a one-to-one function? The answer is no, because look, I can draw a horizontal line here and it crosses the graph more than once. Okay, so A is not 1-1. Okay, because I found a horizontal line that crosses the graph more than once. But B is, because look, if I draw horizontal lines, no horizontal line will cross it more than once. Okay, so B is one-to-one. Okay, and how does this relate to the definition of one-to-one? Well, essentially, we have the input of -2 getting mapped to 1. We have this input here getting mapped to 1, and we have this input here getting mapped to 1. So we have distinct inputs, -2, 0, and 2, but they're all getting mapped to the same output. So distinct inputs are not getting mapped to distinct outputs. So we're violating the definition of one-to-one. Okay. All right. So I'll move on if there are no questions about this. There'll be practice on the homework, which is good. All right. Next, we just want to talk about finding function values from a graph, and table. Okay, so let me go back to my images here. Okay, so we could also find function values from a graph, all right? So part A is asking us to evaluate f of 2, okay, f of 2. So how would we do this? Well, all you need to do is just go to 2 on the x-axis and just see which y value it got sent to. So 2 got mapped here, and what's the y value associated to it? It's 1. So f of 2 is 1. All right, so I hope everyone sees that. And we can also solve. So B is solving f of x equals 4. This is just asking us which input got mapped to 4. So all you do is you go to the y-axis, you go to 4 on the y-axis, and you see which inputs got mapped to it. Okay, so we see that 3 got mapped to it and also -1. So x equals 3 and x equals -1. So it has 2 solutions.
So in this case, it's an and, because the other time you said it should be like an or, like for the quadratic equations, but this one can be an and or like should be an or as well. I don't know.
Right. No, that's a good question. I think it's and here.
Okay, thank you.
Sure. Yeah, but yeah, I'll try and think about that more. But regardless, that shouldn't mess up your answers or anything, but I think it's end. All right, so I hope everyone sees I just went to 4 on the y-axis and saw which x values got sent to it, and it was -1 and 3. Okay. All right, we can also do the same thing from a table. So let's do that. Okay.
Oh.
Okay. All right, so we can do the same thing in a table. So evaluate a G of 3. So the top row are our inputs, and the bottom row are the outputs. So we just want to see what we want to see the output associated to 3. So we go to the input 3, and we see that the output associated to it was 7. All right. So I hope that's okay. And B, solve G of n equals 6. We ask ourselves which input got sent to 6. Well, we see that 2 got sent to 6 and also 4 got sent to 6. So the answer would be n equals 2 and n equals 6. Okay, and just a quick question, is G 1-to-1? So why don't we think about that for a second? Is this function G 1-to-1? Do distinct inputs get mapped to distinct outputs?
No.
No.
I don't think it's 1-to-1.
No.
No. Yes, that is correct.
Yeah.
The answer is no. And would someone just like to explain why? I know there's a few people, so just someone just jump in.
Because G of n has 2 values that are equal to 6 and 2 values that are equal to 8. So it wouldn't pass the horizontal line test.
Exactly. Right. So exactly what you said. So we have, for instance, we have 2 does not equal 4, but G of 2 does equal G of 4. So on a graph, that would fail the horizontal line test. But also symbolically, we see that distinct inputs do not get mapped to distinct outputs. Very good. Okay, next. So we're just kind of going through like a bunch of little topics here. Next, we'll just do solving functions algebraically. All right, so the answer here was no. Okay, so we solved functions from a table, and we also solved them graphically. Let's just do a few examples solving them algebraically. Okay, so example, let f of x let f of x equal x squared plus 2x. So this is a valid function. And the question is to solve f of x equals 3. All right, and what this means is that we need to find which x values, I put the s in parentheses because there could be more than one. We need to find which x values produce an output of 3. All right, so this just comes down to solving. So we solve. So we set x squared plus 2x equal to 3 and solve. All right. All right, and this is actually a question that we have considered. So basically, this is a quadratic equation, and we're just going to factor and solve. So you can bring the 3 to both, you can subtract 3 from both sides. X squared plus 2x minus 3 is 0. So this factors as, sorry. Yes, you want to find two numbers that add to 2 and multiply to -3. And the numbers that work here are +3 and -1. Okay, so I hope everyone sees this. This was just by factoring. All right, and next we use the zero product property. So this is now, we know that x plus 3 is equal to 0, or x minus 1 is equal to 0. Yeah, so here's that business with or and. I'm not exactly sure. But regardless, let's just kind of put that aside for now. This is easily solvable. This is x is equal to -3 and x is equal to 1. So those are our solutions. Very good. All right, so that's it for solving. Okay. So any questions? So we're using some content from earlier in the year, earlier in the semester. Okay, next, very important topic. Okay, next, let's talk about domain and range. Domain and range. Okay, so we have two very important rules in mathematics. Okay, so in mathematics, we cannot do the following, okay? And the first thing we cannot do in mathematics, it is a sin, is to divide by 0, okay? So we cannot divide by 0. All right, so I think everyone kind of knows this already. If you divide by 0, some crazy stuff happens. For instance, if you do allow to divide by 0, you can prove that like 3 equals 4. Like some nonsense like that. So if anyone would like to see this at a later time, I can show you that, which is pretty cool. So that's why we don't allow division by 0, and for other reasons. But one reason is because you can prove that 3 equals 4, which is obviously nonsense. So we don't allow it. I know, it's silly, right?
In fact, that kind of makes sense now, because I was watching a video once where there was some professor, he was saying that, okay, I'll show you how I can prove 1 equals 2. And he did some kind of weird equation, like 2b equals 1. I'm like, wait, and then he got 2 equals. I'm like, no, that's not true at all.
Yes, okay. I know exactly what you're talking about. I've seen that video before. Yeah, essentially in that video, I think he had A is equal to B, which
Yeah.
would mean that A minus B is 0, and then he divided both sides by A minus B, which is the same as dividing by 0. Yeah. Yeah, I've seen that before. It's cool. Okay, so that's the first sin of mathematics. The second one is not as bad. The second one is you can't take the square root of a negative number. Okay, so just let me write that and then I'll explain. Take the square root of a negative number. Okay, so I'm sure you're asking, oh, but we did take square roots of negative numbers and we used I. Yes, that's true. However, the functions that we will be considering are functions that have the real numbers as their inputs and outputs. Okay, you recall that when you take the square root of a negative number and you get I, that's a complex number. And the functions we will deal with in this class do not have the complex numbers as a range. Okay, so in our setting, we cannot take the square root of a negative number. Okay, so we're just going to disallow that. All right, so let me just write that quickly. So, so in more advanced areas of math, so I just want to say that 2 is not impossible. You can do 2. So in more advanced areas of math, we actually can do 2, meaning we can take the square root of a negative number. So these are functions that output complex numbers, and this is a very beautiful branch of mathematics called complex analysis. All right, so that's the setting in which you can do things like that. Okay. But we're not there, so we're going to disallow it for now. Okay. All righty, so we have our 2 rules. We can't divide by 0. We cannot take the square root of a negative number, and this will come into play when we figure out the domain of some functions. All right, so let's see how this works. Okay, consider the function f of x equals 3 over 2 minus x. So 3 over 2 minus x. Okay, so we see that plugging in x equals 2 is bad. Okay, plugging in x equals 2 would cause division by 0. Okay, and is thus not allowed. Okay, so we see that for this function, plugging in x equals 2 is bad. Okay, we don't want to allow 2 to be an input for this function. So we must exclude x equals 2 from the domain. From the domain of f of x. Okay. So x equals 2 is bad because it would cause us to do 3 divided by 0, which is not allowed. Okay, so what is the domain of f of x? So the domain of f of x is all real numbers except 2. Except 2. Okay, so you can see that any other number is totally allowed in this function, 3 over 2 minus x. The only trouble spot is x equals 2. All right, and then we just want to put this in interval notation so we can get more practice with that. In interval notation, how do we notate every number except 2? That's going to be minus infinity to 2 union 2 to infinity. Okay, very important is the use of the parentheses around 2. We're not including 2 in our set, so I need to put parentheses and not brackets. All right,
So the graph will so the graph will just continue, but it will not reach 2.
Okay, so on the graph of this guy, you're going to see something called an asymptote.
Mm-hmm.
We're going to get to later. So it's going to be like this line on the graph that the function actually never touches.
Mm-hmm.
Yeah, we're going to see that later, but you'll see something called a vertical asymptote at x equals 2.
Okay.
All right, good. So we have found the domain. It's negative infinity to 2, not including 2, union 2 to infinity. Let's do another one. Example. Find the domain of the square root of x plus 7. All right, so remember, we're not allowing to take square roots of negative numbers now. Okay, we're not allowing the use of I. Okay, all right, so since there is a square root, we need to make sure the radicand is greater than or equal to 0. Okay, and the radicand, just recall, it's the expression that appears underneath the square root sign. So it's x plus 7. Okay, and this is not bad. All you need to do is solve the inequality. So we solve the inequality. We just solve x plus 7 greater than or equal to 0. Okay, and the solutions to this will be precisely the domain of our function. Okay, because we're figuring out which x values make the radicand, x plus 7, greater than or equal to 0. These are going to be the x values that will produce a non-negative square root. Good. So this is an easy inequality to solve. Subtract 7 from both sides. X is greater than negative 7. Okay. And now just put it in interval notation. So the domain is, it's all numbers greater than or equal to negative 7. So we're allowing negative 7, so I put a square bracket. So it's negative 7 to infinity. All right, so all of the numbers in this interval produce a positive square root, a positive number underneath the square root. Okay, so here's another example. Find the domain of f of x equals x squared minus 1. Okay, so what's up with this example? We need to check for dividing by 0 and we need to check for taking the square root of a negative number. Is it possible to do that in this function? Can we ever divide by 0 or take the square root of a negative number with x squared minus 1? No, okay, because we're not dividing anything and there's no square roots, okay? So the domain is going to be all real numbers. There's no restrictions. Any number is permissible to plug into this function, right? So let me just see if I can write that quickly. Yeah, so there's no danger of dividing by 0 or taking the square root of a negative number. So all numbers are in the domain. Okay, so how do we do this in interval notation? That's just going to be minus infinity, comma, positive infinity. This is how we represent the whole entire number line in interval notation. Minus infinity, comma, positive infinity. Okay, so that is the domain. All right, so any questions? All right, so we went through a few concrete examples. I'm just going to write down the set of steps, and then we'll do another example. All right, so here are the steps. All right, 1, identify any restrictions on the input, okay? Meaning, if there is a denominator, set the denominator equal to 0, comma, solve, and exclude those values from the domain. Okay, so you set it equal to 0, and then whatever solutions you get from that, you exclude from the domain, okay? Because that would cause you to divide by 0, so you exclude it. Okay, 2, if there is a square root, set the radicand greater than or equal to 0 and solve, just like we did. And 3, write the domain in interval notation. All right. So I just wrote out the formal set of steps that we used to complete the first previous examples. That's really all there is to it. All right, we're going to do one more. All right, so here's a slightly trickier one. All right, find the domain of this function, f of x is equal to, so it's going to be the square root of x minus 6 divided by the square root of x minus 4. Okay, so first of all, we have square roots, which means we're going to need to set the radicands to be greater than or equal to 0. Okay, so let's solve that first. Solve. So you solve x minus 6 is greater than or equal to 0, and you also solve x minus 4. Okay, here's where you need to be careful. The second one, x minus 4, you need to set to be strictly greater than 0.
Oh, yeah, you're on the
Okay, and why is that? It's because we don't allow a 0 in the bottom, okay? We don't want this to be greater than or equal to 0. We want it to just be greater than 0. So we solve these guys. So the first one is x is greater than or equal to 6, and the second one is x is strictly greater than 4. Okay, which one is our domain? Which to choose? Which to choose? Okay, now you need to be careful. You need to think for a second. Well, the values for 6, let me write that a little neater. Well, the values in the interval 4, 6 will make the square root of x minus 6 negative. So I hope everyone sees that. If I plug in a number from this interval, 4, 6, that will make the square root negative. All right, so we must choose x is greater than or equal to 6 for the domain. All right, and an interval notation, that's bracket 6, infinity. So that's an interval. All right, so let's just recap. Why was x greater than 4 not our domain? It wasn't because there are values in this interval that will produce a negative in the square root, x minus 6. All right, so we needed to think a little more. So we take x greater than or equal to 6. That takes care of everything. No square roots will be negative, and we will not divide by 0. So we take this one. All right. All right. So, yeah. All right. So I'm going to skip some stuff. So, trying to think. All right. So I'm going to skip these topics. I'll either do them in the next lecture or I will post videos that I find online for them. So I'm going to skip set builder notation. And what else am I going to skip? And, finding domain and range from graphs. So I'm going to skip these 2 topics in the interest of time. However, I will post some short videos that I find on the internet pertaining to these 2 topics that you guys can watch. All right. So videos on Moodle. All right, so I'll post that as soon as possible. I just have to go and find some good ones. All right, so we'll skip that. And we will just end with something that I think is more important, which is piecewise defined functions. Piecewise defined functions.
It's right here. Oh, I wasn't there.
Okay, so we just need a definition. So definition. Okay, so sorry, there's a lot of writing tonight. A piecewise function is a function in which more than one formula is used to define the output over different regions of the domain. So before we had a function for, say, f of x equals x squared. No matter what input we chose, the output was to just square it. However, we'll now chop up our domain into pieces and do a specific formula depending on which piece of the domain we're choosing from. All right, so let's just see what that looks like. So example, f of x equals, so you write it like this in curly brackets. So f of x equals x squared if x is less than or equal to 1. And it will be just x if x is greater than 1. All right, so depending on which area of the domain we're choosing our inputs from, that will determine which output formula we're using. All right, so just some examples. So f of -2. Okay, -2 is less than or equal to 1. So I'm going to use the x squared formula. So that's going to be -2 squared, which will be 4, because the input x equals -2 is less than or equal to 1.
You could use any value lower than or equal to 1.
Yes.
Okay.
Any value less than or equal to 1, I will use the x squared formula. All right, how about this one? How about f of 3? Okay, which formula will I use for 3? Does someone want to tell me and why?
Fx equals x because it's greater than 1.
Exactly, thank you. Yes, 3 is greater than 1, so the formula tells us I ought to use just the function x. So that's just going to be 3. So similarly, because the input x equals 3 is greater than 1. All right, and just a quick sketch of the graph. So it's going to look like a parabola. Yes, this is going to be a very bad drawing. It's going to look like a parabola up until x equals 1. But then past 1, it's just going to look like a straight line, if I can do that. So it's just going to look like a straight line past x equals 1. All right, so not the best drawing, but I hope it makes sense. All right, where are we at? Where are we at? Okay, so we're going to end off with just a nice, we'll do another example, but in a different flavor of a piecewise function. All right, so just a lot of writing, but it'll be instructive. All right, so a museum charges $5 per person with a group of 1 to 9 people. Okay? So if you're going into this museum and you come with 1 to 9 people, they're going to charge you 5 per person. All right. Okay, so if the group is 10 people or more, the museum charges a fixed fee of $50. So if you go into this museum and you come with 10 or more people, they're just going to charge you $50 no matter what. All right, so it's a fixed fee or a flat fee. All right, so so the task is to write a function, call it C of n, that inputs number of people and outputs the price. Outputs the price of entry into the museum. Okay. So we want to just construct a function that will take in the number of people in your party and will output the price for you guys to enter. All right, this is not that bad. So this is going to look like C of n is equal to, it's going to be a piecewise function. Okay, so we're going to chop our domain up into these pieces. So first of all, if n is between 1 and 10, not including 10. So if we come in with 1 to 10 people, not including 10, the museum will charge us 5 per person. Okay, so that would just be 5 times n.
Could you also make that less than or equal to 9?
Yes. Yes, same thing, definitely. Maybe that's a little better.
No, I mean, it doesn't really matter, though. I mean, you could use either, but...
Yeah, I'm going to change it to that, though. That's definitely more clear. Yeah, so if you come in with 1 to 9 people, including 9, it's going to take your number of people and multiply it by 5. That's how we'll get the price. All right, how about if n is greater than or equal to 10? So if you come into the museum with 10 or more people, they're just going to charge you a flat fee of 50. So that's just going to be 50.